Hi everyone. In the last lecture, we solved one problem on radiation shield. In today's session, we will try to solve few more problems on radiation shield. We will try to solve another problem on shields. Problem says emissivities of two large parallel plates maintained at temperature T1 and T2 Kelvin are 0.6 and 0.6 respectively. Heat transfer is reduced 75 times when a polished aluminum radiation shield of emissivity 0.04 are placed in between them. Calculate the number of shields required. It's a very interesting problem. There are two plates at temperatures T1 and T2. Okay, right. Now we are putting few numbers of shields in between the two plates. By putting them, the heat transfer reduces by 75 times. Heat transfer is reduced 75 times. In that case, what should be the number of shields? We have to find out number of shields which will give us 75 times reduction in heat transfer. That's what we are going to calculate. Very interesting problem, but simple problem only. So emissivity of the first plate, epsilon 1 is given. Emissivity of the second plate, epsilon 2, that is also 0.6. And shield, whatever shield we are going to put it, its emissivity epsilon 3 is given. It is 0.04. So we are going to place many shields having an emissivity epsilon 3 of 0.04, right? Finally, we have to get 75 times reduction in heat transfer. Okay, we'll see. We have to find number of shields to achieve this. So this is the formula for heat transfer between the two plates in the absence of any shield. No shield is there. So sigma into A into T1 power 4 minus T2 power 4 into epsilon bar. Instead of putting epsilon bar, I am putting as in the denominator 1 by epsilon 1 plus 1 by epsilon 2 minus 1. Okay, right. And this is a formula for heat transfer between the two plates 1 and 2 when there are n number of shields. This formula I have already given you in one of my previous lectures. Please go through. So Q is equal to sigma into A into T1 power 4 minus T2 power 4 divided by 1 by epsilon 1 plus 1 by epsilon 2 plus 2 times n divided by epsilon 3 minus n plus 1. Here small n represents the number of shields. Epsilon 3 represents the emissivity of the shield. Okay, right. So it is given in the problem that heat transfer without shield divided by heat transfer with shield is equal to 75. That is 75 times heat transfer reduced. Now substitute the expression for Q without shield and Q with shield from the above two expressions. So this by this will be equal to 75. Here sigma into A into T1 power 4 minus T2 power 4 is common in numerator and denominator. You just cancel that, right? And you will get 1 by, if you simplify that, you will get 1 by epsilon 1 plus 1 by epsilon 2 plus 2 times n by epsilon 3 minus n plus 1 divided by 1 by epsilon 1 plus 1 by epsilon 2 minus 1 is equal to 75. Now you substitute the values of epsilon 1, epsilon 2 and epsilon 3. Only unknown is small n. You just simplify, you will get n is approximately equal to 3.52. That is, you need 3.52 number of shields. We can't have in decimal fraction. So we have to provide 4 numbers of shields. So number of shields required is 4. Understood? So another interesting problem. Again, it is on radiation shield only. The problem says two large parallel planes at 800 Kelvin and 600 Kelvin have emissivities of 0.5 and 0.8 respectively. We have two large parallel plates 1 and 2. Their temperatures are given and emissivities epsilon 1 and epsilon 2 are given. A radiation shield having an emissivity of 0.1 on one side and an emissivity of 0.05 on the other side is placed between the plates. So far we have seen the shields having same epsilon 3 on both sides. See, this is the shield, okay, right. On both sides it was only epsilon 3, same emissivity. But in this problem it says both sides have different emissivities. This is possible by using selective coatings, right? So on left hand side, emissivity epsilon 3a, let us say, is 0.1. And emissivity on the other side, right hand side, epsilon 3b is 0.05. This is what is new in this problem, right? Yes. Otherwise, procedure is same. We have to calculate heat transfer rate by radiation per square meter per unit area with and without radiation shield, and we have to comment on the results what we obtain. So what's given? T1 is given, T2 is given, epsilon 1 is given, epsilon 2 is given, epsilon 3a is 0.1 and epsilon 3b is 0.05. We have to find heat transfer without radiation shield and then with radiation shield, and we have to comment on the results. Right. So first we'll calculate heat transfer without radiation shield. You know the formula for heat exchange between two plates. In the absence of radiation shield, Q1 to 2 is equal to epsilon bar into sigma into A into T1 power 4 minus T2 power 4. Epsilon bar is 1 by epsilon 1 plus 1 by epsilon 2 minus 1. Substitute epsilon 1 and epsilon 2 as 0.5 and 0.8 respectively. You will get epsilon bar as 0.444. We substitute, we are considering unit area. So sigma Q12 divided by A is equal to, this is sigma epsilon bar sigma T1 power 4 minus T2 power 4. So we'll get heat transfer per unit area is 7.048 into 10 power 3 watts per meter square. This is the amount of heat transfer occurring between the two plates in the absence of radiation shield. Now let's proceed to calculate heat transfer with shield. Right. So please remember, emissivity of the radiation shield is different on different sides. First, we consider heat transfer between the plate 1 and the left hand side of the shield, that is 3a. So Q1 to 3a is equal to epsilon bar between plate 1 and the side 3a of the shield into sigma into A into T1 power 4 minus T3 power 4. Right. So formula for epsilon bar, you know, so I am putting it in the denominator. So 1 by epsilon 1 plus 1 by epsilon 3a minus 1 actually. Right. I am considering the emissivity of plate 1 on the left hand side of the shield. Similarly, I try to write the expression for the heat transfer between the other side of the shield and plate 2. That is Q between 3b and 2. So that is equal to epsilon bar between 3b and 2 into sigma into A into T3 power 4 minus T2 power 4. So I can write sigma into A into T3 power 4 minus T2 power 4 divided by 1 by epsilon 3b plus 1 by epsilon 2 minus 1. We are considering the right side of the shield and the plate 2. We know whatever heat is transferred from plate 1 to left hand side of the shield must be equal to the heat transferred between the right hand side of the shield and the plate 2. So Q13A must be equal to Q3B to 2. So substitute the expressions for both the heat transfer. This is equal to this, and sigma and A are common, you just cancel it. Then substitute all the values, only unknown is T3. If you simplify, you will get T3 as 746.60 Kelvin. That is the temperature of the shield. Once you know the temperature of the shield, substitute and you can find out heat transfer without shield. Either you can substitute in Q13A or you can substitute in Q3B2. I am substituting the value of T3 in Q1 to 3A. So Q1 to 3A is equal to sigma into A into T1 power 4 minus T3 power 4 divided by 1 by epsilon 1 plus 1 by epsilon 3a minus 1. So substitute the values, I will get heat transfer between the plate 1 and the shield is 509.74 meter square. The same value only I will get as heat transfer between the right hand side of the shield to the plate 2 also. Now let us try to find the reduction in heat transfer due to radiation shield. So Q without shield minus Q with shield divided by Q without shield. And if you substitute, you will get percentage reduction as 92.7. So it means heat transfer reduces by the presence of radiation shield. That is a comment we make on the calculation. Clear? Okay. Go through again, work it out few times. If you have any doubts, please contact me. Thank you.